Welcome to RF transceiver design course. We were discussing about the mixer design from past few lectures, and we have started with the various mixer metrics, mixer parameters, and based on that how can we find out the conversion gain, then noise figure and IP3. So, all we have discussed that what are the different parameters and how we can do the calculate measurement, or we can find out during the simulation all these parameters. Now, we will discuss about the certain topology, how can we make. So, here the first is a balance mixer, which is a RF input matching and RF to LO isolation. So, what do we mean by balance? Balance means if you have a either if your RF is a differential, that means if RF is a 0 and 180-degree phase shift, then it is a balance mixer. However, there is a single balance if RF does not have a differential input, however, LO is a differential, and if RF is a differential, then it is a double balance, fully balanced mixer. So, this mixer is widely used in microwave circuits, and same thing whatever we are going to see, this mixer is also nowadays used in the many high frequency sub terahertz application. So, as we have discussed in the last class that FET mixer, we can either use a FET or a diode, which is a high switch diode, highly switching diode like a Schottky diode. So, which we can also make a mixer at sub terahertz or at terahertz frequency by using this approach. So, this is a in this mixer we need to use a 3 dB hybrid coupler. So, 3 dB 90-degree hybrid coupler. So, what will happen that you will get the difference of the 0 degree and minus 90 degree, and then when you try to sum up, you will get the IF output. Now, let us see how this work. So, before going to the mixer, we should know the what is the S parameter of this 3 dB hybrid coupler. So, in this what is 3 dB hybrid coupler, there is a this is a 4 port device. Now, if you give the RF input at this port, it will through to the port 2 and it has a 90-degree phase shift at here. See, similarly, if LO signal is coming here, it has a through signal and it has a 90-degree phase shift here, and when it is both is a combined, you will get the current which is a combined current at the output. So, here the first thing is means there is a two way we can make this coupler, we can make this balance mixer. Now, in the second case there is a minus 90 and plus 90. So, this is a 180 degrees, the total difference is a 180 degree. So, this is by using a 180 degree hybrid coupler. So, we can use a 90 degree hybrid coupler or 180 degree hybrid coupler, and as we have seen that we need a non-linear component in order to do the mixing. So, either it should have a time variance or the non-linearity. So, here diode is used to add the non-linearity, and due to that we will get the mixing, and the multiple mixing component will be filtered out by using the low pass filter. So, there are two diodes are used at the both side, and this is a hybrid coupler. And if you are giving input at port 1, then there is isolation between port 1 and port 4. So, if you have a design the good coupler which is a wideband and it has a good isolation between port 1 and port 4, then we will also get very good RF to LO isolation. that we have already discussed in the last class, that how why isolation is important in the mixer. So, now we will try to analyze by using the equation. So, we will use a 90-degree hybrid coupler for understanding. Same theory you can apply to the 180-degree hybrid coupler as well. So, we have a RF input which is given by VRFT, VRF cos omega RFT, VLOT, VLO cos omega LOT. So, there is a red color which is a VRF and the green color that is a VLO. So, we should know the S parameter of the 3dB 90-degree hybrid coupler. So, this is the S parameter of the hybrid coupler, because this will tell us that what will be the output at different port. So, you can see that this is a we can write it down that this is B1, B2, B3, B4, and then this is a S parameter, and then so same S parameter A1, A2, A3, A4. So, A is the incident voltage. So, if we want to find that how much is a power at port 2, so what we will get is a that is at B2. So, that is given by B2. So, what is a B2? That is a this is S2, S21, A2 plus S. So, this is a 21, 22, 23, 24, S24, A4. So, you can see that if you apply the signal at A2 and A4, at B2 there is a summation S21 into A2 and S24 into A4. So, when S21, so here S21 is a minus 1 by root 2 j. So, in this case S21 is minus 1 by root 2 into j. So, it is going to add the phase shift of the 90-degree phase shift will be added. So, same thing we can write a voltage that is coming at V1. So, what we will get is a here phase shift is considered as a minus 90. So, 1 by root 2 VRF cos omega RFT minus 90. So, this J is nothing but minus 90, and here there is a minus 1 by root 2. So, it is a plus, it is a 180-degree phase shift. So, what we are getting is a VLO cos omega LOT minus 180. So, it is the same thing A2. So, we have multiplied S21 with cos omega RFT which is at port 1, we have multiplied with S2 cos omega LOT with S24, that is a minus 1 by root 2. So, 1 by root 2 we can take it as a at the output. This is a voltage across the diode 1, that is why it is mentioned as a V1 voltage. Now, if we use the trigonometry cos theta minus 90, you can write it a sin theta, and cos theta minus 180 you can write a cos. So, same thing VRF sin omega RFT plus VLO cos omega LOT. Now, we try to see the voltage across the V2. So, voltage across the V2, that means it is a B3. So, B3 you can see that it is a S31A2. Oh, it is S31A1, sorry. It is S31A1 plus 3 4 A 4. So it is the same. So in previous also it is a A1. So we have multiplied with the VRF cos omega R of t, and we got this term. And for port 4 we got cos omega L O t minus 180. So this is a A1, and A1 is multiplied with this, and A2 is multiplied with this. Now in when we are seeing at a port 2, or when we are seeing at a port 3 and voltage across the diode 2, we will get VRF cos omega RF t minus 180, that is due to this minus 1 by root 2, and VLO cos omega LO t minus 90, that is a minus 90, that we minus j by root 2. So same thing, if we use a trigonometry, we will get a minus VRF cos omega RF t plus VLO cos omega LO t. So this is a what we got is a combination of a RF and LO signal at both V1 port and V2 port. Now what we need is a how the diode behaves. So we will try, we will consider diode is a square law device, and based on the this is a constant k and V1 square. If we consider only V1 square, it has many other terms also, but if we consider only V1 square, your I1 t, that is the current I1, which is square of this term. So that we will get VRF sin square omega RF t minus 2 VRF into VLO sin omega RF t cos omega LO t plus VLO square cos square omega LO t. So same thing if you write it down for the I2 current. The only difference between I1 and I2 current, because we have changed the diode connection, for one it is a positive and for one another it is a negative. You can there are two ways. So in many books you might find that the current direction is shown differently, but you can if you show the same current direction, you should put a negative sign, because we are going to add this current. So when you add I1 plus I2, so what will happen, that we will have a the terms, there are many terms that will be cancelled out, and this sin square and cos square. So we have a V plus cos 2 omega RF t by 2. So cos square can be, cos square and sin square can be written in terms of a 1 plus or 1 minus cos 2 omega RF or omega LO t. So that is why this two term cos 2 omega RF t is coming with respect to sin square, and other is a DC quantity, that is a neglected, because we are going to filter out. So this is a twice of the omega RF, this is a twice of the omega LO. So it is a omega IF, and when cos omega RF and sin will multiply, when this will be added, you will get a sin omega IF t. So this is how the mixer will work. We will get the IF frequency output, that is a sin omega IF t, and this 2 omega RF and 2 omega LO can be filtered out. So that is why here the filter is very important in this circuit. So this filter, low pass filter, is important, so that it can filter out all other frequency component that is a not a desired frequency component. So we can write a IIFT, which is a minus k VRF into VLO sin omega IFT. Now we will try to see that how the reflection means what is the input impedance or the return loss at the input side that we will get. So there is a V gamma 1, which is equal to gamma into V1. So gamma is a reflection coefficient, it is equal to minus a by root 2 gamma into VRF. So here if we try to see that if there is a reflection voltage here due to the diode is a V gamma 1. That V gamma 1 we can write it as a gamma into V1. So, gamma which is a reflection coefficient into V1 which is given by minus A by root 2 gamma into VRF. So, if you consider the RF voltage, it is a minus A by root 2 gamma into VRF. Similarly, we can write a V gamma 2 at the uh, at the diode 2, it is given by gamma V2 which is equal to minus gamma by root 2 into VRF. So, what we can see is if this is a 4 port, this is 1, 2, 3 and 4. So, whatever signal that you have applied here, this is a VRF, it is going to have the minus J by root 2 here, and the same thing at port 3 you will get a minus 1 by root 2, means your reflection will have means multiplication of that term minus J by root 2 and a minus 1 by root 2. That is a reflection voltage at diode 1 and this is at diode 2. So, when you write a gamma means when actually how much reflection you are getting at the input, what is happening, the because your coupler is a uh, symmetric and whatever input you will get at the output port, same you will get means the performance will be based on the S parameter. So, if you give the input at port, the combination of port 2 and 3 will come at port 1. So, same thing we can write a minus J by root 2 into V into gamma 1. So, if you apply at port 2 voltage, minus J by root 2 into V into gamma 1 voltage will come, and minus 1 by root 2 into V into gamma 2. So, when we try to use the same we keep the same voltage V gamma 1 and V gamma 2 in this equation, what we will get a minus 1 by root 2 gamma VRF plus 1 by root 2 gamma VRF, it is equal to 0. So, what it says that for all the frequency means at which your coupler will give this behavior, that is a 90-degree hybrid coupler, and if it satisfy this S parameter, we can have a return loss at the RF it is equal to 0, means there is a no reflection. So, it is very helpful for high frequency because if your input port is matched, your coupler port is matched, then your there is no reflection occur at the input. Similarly, we can see for the V gamma LOT, and at V gamma LOT there is a reflection, means we will get a RF signal which is J into gamma into VRF T. So, that is again it is based on the how much isolation between VRF and VLOT. So, this is how this mixer will work, and we can design FET based mixer. Instead of using the diode, we can also make a FET based mixer and it can also work. So, this was used in widely used this mixer in the microwave mixer design, but you can also incorporate the same thing at very high frequency on chip RFIC design, where you need to design a hybrid coupler, and there are many methodologies by which you can design a hybrid coupler on chip, and we have already seen by while discussing the inductor, we have seen a transformer. That transformer can also used to design a hybrid coupler. So, this is one way balance mixer can be realized by using a diode or FET. There is another configuration, that is the image reject mixer. So, in this what we have studied while discussing the image reject receiver. So, same thing, that is a Hilbert transform. So, adding a 90-degree phase shift, and in that what we have considered is a RC CR combination to provide the 90-degree phase shift. Now, why can't we use a hybrid coupler to do the same? So, what is the advantage of using hybrid coupler? The advantage is it can provide a wide bandwidth, it can also work at very high frequency. Your RC has a loss, however, there is a insertion loss is there in the hybrid coupler also, but the matching is very good. So, here what can be done, that 90-degree phase shift which is here, we can bring it at the input side. So, this 90-degree phase shift is a bring it at the input side. So, your RF input here, this is a RF input, and then there is a 90-degree hybrid coupler. So, what it will do is this 90-degree hybrid coupler will divide the signal into 0 and 90. So, what is the advantages in this, that here you are using the sin omega LO and cos omega LO, that is the quadrature signal, you are generating a quadrature signal. However, a quadrature LO signal, however, in this case you have a quadrature RF signal. So, this LO does not require a quadrature input, your RF itself is converted into the quadrature. You can also make design where LO is a quadrature and RF is a single ended, where your RF and then LO is multiplied with the quadrature. But what will be advantages here, that your RF will also be matched as we have discussed in the last mixer, that is a balance mixer. So, now this what will happen, that when you want to do the addition, so this adder is also replaced by the coupler. So, coupler here will also use to do the addition of the two signal, and we have already seen in the last class that if your B1 or B2, it is a combination of the signal at port 1 and port 2. So, if you are seeing at port 2, it is a signal combined from which is coming from the port 1 and port 4. Similarly, you can get at V2 port 1 and 3, only there is a phase difference, and due to that what will happen, that you can either tap a lower sideband. If you tap from one side, it will give you the lower sideband. If you tap from another side, you will get a upper sideband. So, one of the signal will be image and one of the signal will be your actual signal. There is a possibility that you can make a two band at the same time, one is the upper sideband is one band and lower sideband is another band. So, you can use it as a dual band receiver. So, this has a multiple application, this image reject mixer. Now, we will try to see that how this upper sideband, means we will try to calculate that how upper sideband and lower sideband can be differentiated. So, it is the same thing that we have discussed while discussing the Hilbert transform, how it is rejecting the image. We will try to use a trigonometric function to get the same output. So, VRFT, we can write it down as a VU. So, if let us say there is a, this is omega LO and there is a one signal that is called upper sideband, that is at high frequency, that is omega RF. So, omega LO plus omega IF. So, this is a omega if, and there is another signal if you consider it as a image, that is a omega if, means omega im image, and this also have a difference of the omega if. So, what I can write is, if the voltage of this is given by V u, that is upper sideband voltage, omega LO is at the center, the right hand side which is a higher frequency than that is called upper sideband, and the lower frequency on that is called a lower sideband. So, the upper sideband, so V u, that is the upper sideband voltage into cos omega LO plus omega f, and V L cos omega LO minus omega if. So, this is a V L and this is a V u, voltage which is upper sideband and voltage which is a lower sideband. So, we can represent the entire band which consists of both upper sideband and lower sideband by using this equation. Now, V A, the voltage at port A. Now, when we see the voltage at port A, same thing, there is a 90-degree phase shift on the upper sideband, V u cos omega L O t minus omega R f t minus 90, and V L cos omega L O t minus omega f t minus 90. So, here this equation when it is written, it has been considered. So, you can use a last example, whatever we have discussed, that if you have a VRF which is applied and this is a mixer. Now, here this mixer you can use any mixer, that you can use a diode based mixer, you can use a FET mixer, and whatever mixer that you want to realize, you can realize, but it should have a multiplication function, and once it is multiplied, it is a low pass, that is a VIFA. So, the VIFA is a filtered and a mixed output. So, that is why it has only written a V omega RF minus omega L. So, it is a two thing, because it is a 90-degree hybrid coupler, it is a phase shift by 90, but you will have a omega LOT minus omega RFT minus 90, omega LOT minus omega IFT minus 90. So, what you will get is a V upper sideband omega LO plus omega IFT 1 by root 2 V u cos sin omega LO plus sin omega LO plus omega IFT, and V L sin omega LO minus omega IFT. So, what we will get is a combination of LO plus omega IF and omega LO minus omega IF, that is upper sideband and this is a lower sideband. So, here we have down converted both RF as well as image. Now, VAT at port B means here there is. So, at port B we can also write 1 by root 2 V upper sideband cos omega L plus omega F minus 180 and VL cos omega L t minus omega F t minus 180. So, at port, when we consider the voltage at port B means VIP, what will happen here, this is a matched. So, when you see the output at port 3, it is a combination of this RF and then this LO which is a multiply, that is a cos omega LO t. So, this VRF A and VRF B we can find out by using this as parameter. So, if at port 1 it is applied, at we will get a B2 which is a S21 A1 and B3 which is a S31 A1. So, that is why for one it is a minus j by root 2 and for another it is a minus 180. So, same thing, we will write a VB where only minus 180, here we have considered minus a by root 2, that is why minus 90, here it is a minus 180. So, when you consider minus 180, it is a minus 1 by root 2 cos omega LO plus omega I f t plus V LO cos omega LO minus omega I f t. So, this is a VA and this is a VB voltage. So, your if you consider the S parameter, which is this minus 1 by root 2, same S parameter that we have drawn, your VIFA equal to at this point minus j k VLO 2 root 2 VU minus VLO sin omega IFT. So, here VIFA, this is a filtered output. So, how this is a filtered? So, here when you multiply with a this with a cos omega LOT, and when you multiply this with a cos omega LOT, you will get a sin omega IFT, because this omega LO and cos and sin will be multiplied, you will get a sin omega IFT, where this is VU upper side band and this is a minus VL, that is a lower side band. At VIFB you will get a minus k VLO 2 root 2 VU plus VL cos, it is a cos omega. So, there is a quadrature signal, it is a cos omega IF t. So, there is a sine, means sine and a cosine. So, one is a sine omega IF t and another is a cos omega IF t. So, when you try to add this two, you will get a VIFA. So, if you consider only the magnitude and VIFB, so this is a VIFA where j by 2 root 2 k into VLO VU minus VL, and at V1 what we are getting is minus j by root 2 minus VIB by root 2 k VLO plus VL 2 into LSB. So, what is happening here, that if you see the S parameter, so at same 90 degree is used at the output also to combine. So, that is why here the VIF has a minus j by root 2 which is added here, and here minus 1 by root 2. So, this is a 90 degree and this is a 180 degree phase shift. So, V1 which is a combination of minus j by root 2 VIFA minus VIFB by root 2. If you write VIFA here, so if you consider j by root 2 and j by when j by root 2, so we can write it down V1 which is equal to minus j by root 2 into minus j by root 2 k j by 2 root 2 k into VLO VU minus VL minus VIFB. So, 1 by root 2. So, this is minus minus plus, we can write 1 by root 2 and k by 2 root 2, same VU minus VL. So, here this j will be cancelled out, this is a plus sign. So, there is a 1 by 2 into root 2 4 and k into VLO, and you can see that this is a VU minus VL. So, 1 is a, and when j square it is a minus. So, VU is a cancelled out. and we will have a VL. So, because Aj square it is a minus 1, we will have a VL minus VU plus 1 by 4 K VLO VU. So, this is a VU plus VL. So, VU will be cancelled out and we will get a K VLO VL by 2 into VL. So, this is oh sorry K VLO VL by 2. So, same thing you can do for the second port, and it is a, this is a final output that we will get, which is a cos omega ft and sin omega IFT, that is the upper band, lower side band and the upper side band. So, this is how this image reject mixer will work, and you can find out the both upper side and lower side band. We will discuss more about the mixers and various topology of mixer in the next class. Thank you.